There we go. And then go to multimedia. And then turn off the mic, the internal mic. There we go. Okay, because if I don't turn off the internal mic, I think one of the channels is still recording the internal mic, which is going to be an issue. And then turn the resolution to the usual one that I use in this classroom. There we go. Okay, good. All right. So the recorder is on, audio is on. But I just, I came back from an IBM, what they call residency. So I am expected to be there for 2 weeks from 9 to 5 every day. And so I just told them, no, that's not going to happen. The best I can do is to show up maybe for an hour or two each day, and that's about all I can do. Because that place also turns out to be over at Gateway, which is West El Camino. So it's not really that close to ARC. It's not like, I can just kind of hop on over for a few hours and then come back here. But the interesting thing was this, what they call residency, is about, me working with some other people to come up with a course outline for COBOL programming, okay? Which is, how many people have heard of COBOL as a programming language? Some of you, okay, very good. So you might have heard about it from your parents or your grandparents, right? Because the whole idea of why they need so many COBOL developers now is because a lot of the state employees who wrote the programs or at least helped contribute to the programs that are now being used by the Franchise Tax Board, the Department of Motorized Vehicles, EDD, which is Employment Development and something department, okay? But anyway, they still have a lot of code that is currently written in COBOL, and they're not going to go anywhere anytime soon. And it has to do with how they have stored data for the past few decades, okay? For the past 40 years or so, they have been storing data in a form that only COBOL can process easily. So they cannot switch everything to Java or C++ or C#. It's just not going to happen. So for any one of you who want to kind of look into possible, employment with the state particularly, or Wells Fargo, one of the IBM SMEs or subject matter experts also mentioned a few other companies there, and they're still using COBOL. Amex, American Express, is still using COBOL. So we are talking about huge companies, huge corporations, and as well as institutions that still rely on COBOL programs, for their daily, day-to-day, operation. So if you are looking into, employment and you go like, I don't want to go where everybody else is going, okay, because there's a lot of competition where everybody else is going. COBOL turns out to be one of those few areas where there's not a whole lot of competition. Does it make sense? Okay, so that's just kind of something interesting for you guys to think about. Yep.
Can you show us a bit of what COBOL looks like as a language?
Yeah. So you can just look it up. COBOL program examples, right? And we can go for something. So that's kind of what a COBOL program looks like. There's a whole lot of data. This is for presenting something, so it can control the screen. In order to show, to specify what gets displayed where. And if you want to go look at something that works with sequential file. So once again, you have a data section, data division that talks about. That's basically your class definition. Okay, each thing has this as the first thing, this as the second thing, this as the third thing, and so on. And then you have your procedure division, which is basically code. COBOL is one of the programming languages that is super verbose. In other words, you can read a COBOL program without much training and understand what it is really trying to specify. You can't really quite do that with some of the other programming languages, like C and C++, I would say, is on the concise side, okay? But COBOL is not concise. I mean, it is by design, really verbose. So with COBOL programming, it's not about the programming language that makes it kind of challenging. It is, the fact that it deals with data, how it deals with data, that makes it kind of interesting. Okay, some of you, okay, I shouldn't say most, but some of you know how we can access a relational database from JavaScript or Java or C++. That's how we deal with data these days. Okay, most of the time. But COBOL comes from a time when there are no relational database. Even random access file is kind of like, wow, that is new, okay? A hard drive was a novelty after COBOL was invented. So COBOL was basically invented to deal with sequential files. We are talking about, reels of tape. Okay, in those really old movies, when people show computers, they always have some kind of a tape thing, right? That's when COBOL was invented. Okay, so it was invented to deal with tapes. Then you might think, well, that's really old-fashioned. Why would they? I mean, that's totally outdated and not applicable anymore. The funny thing is, it is applicable again. Okay, what about the data that we can now store online? Okay, it's massive, right? Okay, just think about all the traffic that Amazon has logged, okay, over, who knows how many years. There's a huge, massive amount of data. Is that stored in a relational database? It's not, okay? It's stored in a cloud sequentially, okay? So all it does is to say this IP address with this particular cookie went to look at this particular product at this particular timestamp. Okay, it's just a huge sequential file of logs. So a relational database is not going to be very helpful processing all that data because relational databases rely on what we call a join operation, where you have to connect two tables together to form a single query. That is a bottleneck when it comes to not being able to parallelize operations. And as a result, relational databases has actually somewhat run out of steam when it comes to processing huge amount of data. So when it comes to huge amount of data, what does it come in, in the form as? A stream, okay? A sequence of bytes. And guess what COBOL is good at? Processing sequences of bytes. It used to be a tape, and now it's a TCP/IP connection. So I think there are very interesting things that might happen with COBOL programming, just because our technology has now gone back to those older days where you got mainframe concepts again, okay? And you guys would go like, what mainframe are we talking about? I got my cell phone, I got my laptop computer. We're not using mainframes.
I don't want to get you too off topic here, but
Well, we're already way off topic, so it's okay.
what could make a language faster at reading something sequentially than another language?
It's not about the language itself. It is about, it already has features in place. Those features are intrinsic to the programming language itself. And it also has a huge amount of data already stored in the form that kind of program can process. Now, can you present a data set, which is basically a file, to a modern programming language like Python or JavaScript and have those programs to process it? Absolutely. Is it going to be good at it? Well, probably not as good as COBOL, because COBOL is built from the ground up to process that. And for the most part, it's also about the translation of business logic. A lot of that is already coded in COBOL, and these big organizations like Wells Fargo Bank, Bank of America, American Express, they cannot afford to make a simple mistake. The cost of the mistake is far more than the expense that they have to put out in order to continue to use COBOL. So it's a very interesting equation, from that perspective. And also, we also went all the way from mainframe computers and the terminal programs to access a mainframe computer to personal computers that can store your data locally, and you can do all your processing with spreadsheets locally. You can connect to a printer and print your Word documents locally. Back to everything back in the cloud. So we are actually back to the methodology of having centralized processing resources again. So most of you are way too young to kind of make that association because you have not been exposed to the mainframe computers. I barely got exposed to those computers, but we are going back to that method of computing again. So really kind of interesting stuff. So the first thing we'll do is we are going to take a look at the exams again. So we can talk about the solution, then we can move forward and continue with our discussion with relations. Okay. So let's go to the exam. So how was the exam?
Tell us.
Hmm?
How'd we do?
Well, we'll talk about the answers, and you guys can tell me, how you think you did in the exam. Okay, we'll pick this one as an example. There we go. So what do you think is the purpose of this session where we go back to the exam and then we looked at the questions and then we try to figure out what the answers are supposed to be? What is the purpose of doing all this? Okay, and? Okay, well, that's a very pragmatic, way of thinking about it. But I think the most important part is if you did make a mistake, if your answer is not exactly the same as what the correct answer is supposed to be, is it because you did not understand the question? Okay, if you did not understand the question, tell me, because I can try my best to write the questions in a way that that describes what I want. Or, is it because you somehow could not make the connections during the test? Or is it because, the material was missing? Okay, you did not bring, the material with you, in the exam for that particular question. So we'll go ahead and start with question number 1. Okay. So question number 1 is something that is somewhat familiar, with the other two practice exams. So the first one has part 1, define a set W such that each element of W is a digit of your student ID, and the cardinality of W is 3, is true. And there may be many ways to define such a set depending on your student ID. Just pick one, okay? So I was banking on the fact that no one in this class only has 2 unique digits in that person's ID. And nobody came forward to me and go like, I have a problem because my entire ID only has 1 and 7s. Okay, nobody came forward to me to complain about it, so I was thinking, okay, at least everybody has 3 unique digits, in your ID. Okay, so to answer that question, all you have to do is to say W is, okay, so I left some space for you to write down your answer, which is here. The braces are important, okay? If somebody just lists 3 digits without the braces, points will be taken out because, that is the notation of a set, okay? When you tell me what the elements are in a set, you have to use the braces to tell me where it begins and where it ends. So I'm gonna use mine as an example, okay? 0, 6, and 7 are all digits inside my ID. But my ID actually has 3 zeros in it. So what if I put 0, 0, and 0 in here? That would not be good, right? And why not?
Sets can't have redundant elements.
A set can only, all elements of a set has to be unique. Yes?
Even if you put them as a separate set inside the set?
Say that one more time.
So like if you had if you had a set like this,
Mhm.
if you had another element which was a set,
Yeah.
and it had a duplicate in it,
That would be okay.
that's okay.
But the set that I'm asking you to give me,
It's cardinality.
cardinality of 3, and all elements in it need to be digits, not a set of digits of your ID. Yep. So there we go. So 067 is a possible answer. That all depends on your specific ID. So are we good so far? So I think those are pretty easy points to get once you understand what a set is, what is the notation, and what are the limitations. Okay, you can only have unique elements inside a set. All right, so we are moving on to part 2. So part 2 starts with a definition of x, which is all the digits from 0 to 9. And I want you to define a new set y such that all of the conditions are true. Okay, y is a subset of x is true. I want y w union with y is 5 is true, or the cardinality of that union is 5. And I also want the cardinality of w intersecting with y equals to 1. Okay, so let's look at each one and basically see what that means. The first one is pretty much given, right? Unless you have a hexadecimal student ID and you have the letter B in your ID, and that is not a part of the digits from 0 to 9. So the first part is pretty much automatically true. Second part, the union needs to have a cardinality of 5. So that means you need to, your W needs to, your Y, your set Y needs to introduce 2 new elements to make up a total of 5. Okay? So let's go ahead and try to construct our Y, set Y over here. So I look at 067 and I ask, what else can I add to the union that is unique? 1, 2 are missing, right? So I can certainly have 1 and 2 in this case. All right. So that will make the union having 5 elements already. Because now I have 0, 6, 7, 1, 2 in the union. That will make the cardinality 5. I have met the second requirement already. So now I need to meet the third requirement. The third requirement says W intersecting with Y, and if you take the cardinality of that intersection, needs to have 1 and only 1 element. Okay? So that means I need to find something that is common between W and Y, and there's only one thing in common between those two. Okay? So I look at what W already has at this point, 0, 6, 7. Just pick one of those. 7. Okay? So let's say I put 7 down here. That will meet all the requirements. Does that make sense so far? So this question, at least with part 1 and part 2, really is just testing, do you understand how to represent a set? Okay? Do you understand the concepts of cardinality? Do you understand the concept of a subset of? Do you understand what is a union? And do you understand what is an intersection? Those are all just definitions. Are we good so far? All right. So now we move on to part 3, which is also just asking you, do you know what these operators are when it comes to set operations? W minus Y, okay? And what would that be? Everything that is in W that is not in Y. So we look at W, it has got 0, 6, 7. The only thing that it has common with Y is the 7. So in this particular case, 0, 6 will work out, okay? What about the other way around? Well, then it's asking for everything that is in Y but not in W. We look at Y, it has got 1, 2, 7. The only thing that it is in common with W is, once again, the 7. So we take that out. So it is a set of just 1 and 2 in it. The third part asks, what is a value V such that the following is true, okay? It is not the case that V is in W union with Y. And it doesn't even say that V has to be restricted to be in X. It just cannot be in the union of W and WY, those two sets, okay? So a very easy way to answer this thing is not even a digit. That will work, right? Because I did not say any restrictions. I did not say that V even has to be an element in X. Now, let's just say that you it's kind of implied, right? Because otherwise, why would you give us the set of x? Fine, okay. So if that is the case, can someone tell me what is one value v such that it is not in the union of w and y? 3. Okay, we got quite a few choices. Okay, 3, 4, 5, 8, 9. Those would all work. Is that okay? So as you can see, there are many, many possible right answers. Okay, and if I see 2 people turning in exactly the same answers, the likelihood of that happening should be pretty low. All right. What about the last one? I need to find something so that it is in the intersection between w and y. I think we have talked about that particular value quite a few times already. And what is that? 7. Yep. There we go. So that's question 1 of 7, which is really just a test of whether you know where to find the definitions and whether you know how to use the definitions as constraints to answer these questions. So we good with 1 of 5? Okay. Moving on to 2 of 5. Okay, so 2 of 5 once again has several parts. I try to be kind of specific, breaking them into different parts and then use the bullet points to ask, okay, these are the requirements for this part, and then give you the space to write down your answer. So part 1 says define a set W such that each element of W is a digit of your student ID. They go like, hey, that's almost the same as the previous question, but then there's more, right? The other one is all digits of your student ID are elements of W. So that means if something is in W, something is in W if and only if it is a part of your ID. Is that okay? If your ID has it, it has to be in W. If W has it, it has to be in your ID. Are we good so far? So my particular ID is 0006887. So in that case, my W would be 0, 6, 8, and 7. I got 4 unique digits in my ID. So how your answer is supposed to be depends on your specific ID. Okay? Now somebody may say, but my ID has 7 unique digits. It is not fair because I got more to write. Okay, well, I cannot say anything about that. But a few more digits, it should not make that much of a difference in the test. Are we good so far? How many people have 7 unique digits in your ID? Okay, we got a few, just 1 or 2. So later on in this class, okay, just remind me, because we can actually calculate what are the chances that you have an ID that has 7 unique digits instead of having common digits somewhere. So when we get to combinations and permutations and counting, that's when we can analyze all of these things. Okay, part 2, evaluate the expression. There exists E in W such that E mod 2 equals to 0. Explain the results of the evaluation of this. Okay, so this expression here, okay, which is the same as that one, simply is asking, is there at least 1 digit in your ID such that it is even? Is an even number? Okay, in my case, yes. There's a 0, right? And also the 6 and also the 8. So the answer to that is it is true. Okay, but I'm also supposed to explain it. Okay, so when I explain it, I can choose one of the 3 values, and I can say when E equals to, pick one of those 3, okay? 0, 6, or 8, okay? I will just pick 0 here. E mod 2 equals to 0 is true. And because it's an existential quantifier, okay, because it has a there exist, so that means if I can find at least 1, it's good, okay? The whole thing is true. So that is what I'm asking when I ask, explain the result of the evaluation. Okay, now you don't have to say exactly when E equals to 0, E mod 2 is 0. You can say 0 mod 2 is 0, okay? That's fine. As long as 0 is listed over here, I'll count it. Yep.
Do we actually have to say the specific number, or can we just tell you that at least one of them is divisible by 2?
That's fine too. Yep. All right. So this part is supposed to go here, because I have one row, just for the reason. But if you put both into the same row, that's fine, as long as I can find it. Okay. All right. Part 3. Part 3 says evaluate the expression for all e in W. E is less than 8. Okay. So in my case, well, unfortunately, that is going to be false, right? Because I can find at least one value, which is 8 itself, that is not less than 8. Okay? So the answer to that is this is false. And why is it false? Because when e equals to 8, e is less than 8 is false. And if I want to be really complete, which I'm not expecting it from you, when the quantifier is what we call universal, as opposed to existential. Are we good so far? Yep.
Kind of read that expression as every value in W is less than 8. There's like every individual value.
Yep, that's what it's saying. Yep. So in your explanation of why it is either true or false, yep, you just. Yep. So if you use an English explanation or interpretation of the expression and say, oh, that is just not true, that's fine too. Because I just want to know whether you know what the expression means. So you can do it this way. You can do it with just an English explanation. As long as I can see that you understand the expression, then it's going to be okay. All right. So are there any questions about number 2 of 5? No questions? Okay. Let's move on to number 3. So number 3 looks a little bit lengthy, and it is a little bit longer, okay, because it requires you to define functions. So we'll go ahead and read this carefully. Part 1, you can copy this from one of the other questions. Define a set W such that each element of W is a digit of your student ID, and the cardinality is 3. So basically, you can copy from question number 1, okay? But I only said that you can copy and not to copy, because some people may skip question number 1 and jump right on to question number 3. So those people would not have a question 1 to copy from, okay? So we'll go ahead and just say, well, since I did question 1 already, we'll just go ahead and stick with those. Part 2, define y such that 0, 6 is a subset of y. Okay, so y can be just that, but it can also contain additional elements. And then we also want to define a function f. So in this notation, I'm testing whether you understand what this notation means. So in that notation, we know w is the domain and y is the codomain. Okay, so that part is part of what I'm testing you. As a set for each of the following constraints, if you think a particular constraint is impossible, tell me why it is not possible. Okay, so we'll work on these one by one. The first one says f is not injective and it is not surjective. Not injective means it maps 2 domain elements into one single codomain elements, at least 2, okay, into one. Okay, so not surjective means not everything is used in the codomain. Okay, so one way to arrange this is for f to map 0 to 0. It will map 6 to 0. And then we'll map 7 to also 0. Okay, so this alone will make f not injective because it maps every single element in the domain to one thing in the codomain. Is that okay? So now the next question is, well, what do I need to do with y, knowing that y is a superset of 0, 6, to make it not surjective? This alone is definitely not injective already, so we got not injective done. We just need to get the not surjective part done too. But guess what? It's also automatically done because I just mapped everything in the domain to 0. What about the other thing that is also supposed to be in the codomain? Nobody maps to it, right? So 0, 6 is going to work for y in this case. Now, is this a unique answer? Definitely not. You can make y as big as you want, okay? If somebody says, oh, it only took me 45 minutes to answer all the questions, I got lots of time left. You can just give me values after values after values after values as long as 0 is in it. Does that make sense? Because, if you don't want the codomain to be surjective, you just need to make it bigger than all the elements that are currently mapped. Is that okay? On the other hand, if you want to say, I just want the minimal, okay, because I don't have time to write down, all the other extra elements, this is as minimal as it gets. Are we good so far? Okay, all right. So the second part asks, I want f to be injective, but I also want it not to be surjective. Injective means it has to be unique, okay? Everything has to map to unique elements. So that means in this case, I better make sure that my two tuples are mapping things from the domain to things that are unique in the codomain. So now 7 has a problem, right? Because I have just used up everything in the codomain as a subset, okay? 0 and 6 they must be in Y. But the constraint of 0, 6 as a set is a subset of Y opens up the possibility of, but Y can contain additional stuff. We just need to make sure that 0, 6 are in it, okay? But it can contain additional stuff. So I can just say, well, let's put 9 in it, okay? I'm just randomly picking a value 9. So now you have to define Y so that it is not surjective. So we know Y minimally needs to have 0, 6, and 9 in it, because those are the things that appear in F, okay? So everything that appears in a tuple of F as the second item, they all have to appear in Y. But this is not the minimal of Y, because if I made Y this way, it is surjective. So I need to add one more thing that is not mapped to make it non-surjective. So I can pick 1, I can pick anything, okay? As long as it is not mapped to, you can use A, B, C, you can use anything in this case. Are we okay so far with the second case? The third one is not injective, but surjective, okay? So that means we have to use up everything. But we can potentially map two things from the domain to the same thing in the codomain. So for this one, I'm going to be lazy, and we specify Y as minimal as we can, okay, which is just 0, 6. We know 0, 6, they must be in Y because of the constraint that 0, 6 as a set is a subset of Y, okay? So now we go back to F so that we can make it not injective, okay? So we can make 0 map to 0. We can make 6 map to 6. And then we just make 7 to map to 6 also. So now it is not injective. Are we doing okay so far with this? So as you can see, there are many ways to answer these questions. I'm just picking one of many ways to do it. And then the last one says F has to be bijective, which means it has to be injective and surjective at the same time. So I can go back to one where it is injective, okay, which is the second one. Okay, we just copy that as F. So we map 0 to 0, we map 6 to 6, we map 7 to 7. And then when we specify the codomain, we need at least 0 and 6 in it, and this time we just have to make sure that 7 is in it too. So now it is both injective and surjective. Are we doing okay so far with this? Shall we move on to 4 or 5? Okay, all right. So question 4 or 5 requires a little bit of algebra, okay? So let's read the question first. The question says, we basically want to compute g of k plus 1, comma k plus 1 from g of kk, okay? And we want to avoid the use of multiplication or division, because those are slow operations, okay? So the question is, if I maintain g of kk as its own value j, how do I compute g of k plus 1 in terms of j and k and other constants? That's basically what the question is asking. So we doing okay so far with this? Yes? Okay. So I'm going to use this empty area here to work on this one. So we basically want to express k plus 1, g of that, to be g of kk, and do something about it, okay? But we don't want to use g of kk, okay? So we'll just say that plus something here, okay? And we want to find out what that something is, because we know that this is just what we call j. Is that okay? All right. So to find out what that something is, okay, we are basically doing the same thing as this something, which is the same as this something over here, is really just g of k plus 1 minus j, right? And we also know what j is, so we just go ahead and carry out that operation. So now we have k plus 1 plus k plus 1 times k plus 1 plus k plus 1 plus 1, the whole thing divided by 2 plus k plus 1. That is g of k plus 1, We want to subtract, okay, k plus k times k plus 1, the whole thing divided by 2 plus just k. And group that whole thing. Are we doing okay so far with this? Yes? So it does boil down to something that looks somewhat ugly, okay? But not something that you cannot handle, okay? So we'll go ahead and look at this and say, okay, what does that become? So this becomes 2k plus 2 times 2k plus 3 divided by 2 plus k plus 1 minus, this is just 2k times 2k plus 1 divided by 2, the whole thing plus k. Are we doing okay so far? All I did is to group all the k's together so that we can have a multiplication. Now, I know I said no multiplication or division, but we are working on it, right? So it's okay to have divisions and multiplications and squares and whatnot at this point. I just need to somehow reduce the final line so that it doesn't have those things. Okay. So what do we do next? We need to kind of simplify this. You can multiply everything out, okay, and just so that you get the whole thing. So let's go ahead and multiply everything out. So this we got 4k squared plus, is it 9k plus 6, the whole thing divided by 2. And I'm just going to do the plus 1 here because this k cancels out with this k. I don't want to. Should be 10. 2 plus, oh yeah, it should be 10. Okay. So that's one side, and then minus the other side is going to be 4k squared. And then we got just 2k plus 2k, and then plus nothing. Okay, because we don't have a constant itself. So let me just double check, make sure that's right. Yep, that looks good. Divided by 2. We good so far? Yes? So we are just expanding the binomial stuff, okay? So now you can see, lots of stuff would cancel out, okay? So we got, the most important part is the squared cancel out. Phew. Okay. The other stuff doesn't quite entirely cancel out, okay? But we got, we got 5k on this side plus 1 after we divide, that's also the 3, so there's 4. And then minus on this side, we got just 1k, right? Because we got 2k divided by 2, and then on this side, we got 10k divided by 2, that gives us the 5k. 6 divided by 2 is a 3, plus the 1 that is outside, that gives us the 4 as a constant. So when you're done with this, then we end up with 4k plus 4. Are we good so far? And then somebody is going to say, but Tag, you said no multiplication. 4 times k is multiplication. There. No multiplication anymore. Now, you guys might look at this and go like, oh, that is a dirty, cheap trick. Well, guess what? These dirty, cheap tricks is what is going to allow you to use a very inexpensive processor to do fairly complex operations. Okay? Because implementing multiplication as a general operator is very time consuming. Okay? Now, this can also be done by 2 left shift operations, okay? But since I did not mention anything about, yes, you can also use left shift. So if you use left shift, I'll count it as okay, okay? But if you use this solution, or even here, if you get to 4k plus 4, I'll count it as good. Do we have any questions about this one? Nope, okay, yep.
I think I ended up actually using j plus k plus 4. Would that be okay?
Yes, you need to, this is just the difference. So the actual answer is, you express g of k plus 1 as j plus this value. You're correct. This is just the difference. Yep. So the entire answer is this. Oops, not that one. Ah. There you go. But that's kind of cool, okay? Because that means if you have a particular pattern of traversing the pixels to compute the g value, you don't need to do the squared or the almost squared divided by 2 and stuff like that. You can actually just keep adding certain values. That makes it I think that's kind of a cool trick to it. So we okay with question number 4 or 5, which is probably one of the more time-consuming one because you have to remember how to use algebra. Well, that's because that's why we got Math 370 as a prerequisite of this class. That's pre-calc. All right.
People in calc still can't do arithmetic sometimes.
I'm not hearing that. La 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 la. Algebra is really useful, okay? As a programmer, okay? Why do you think, developers, programmers, coders, okay, need to understand algebra? Why is algebra important? All I want to do is to write some games. Yes? Say that one time? Critical thinking skills? Yes. So any type of math class trains critical thinking skills. But algebra actually has a direct application in programming. And what is that? Yep.
Well, I have a funny story about it.
Go ahead.
So, in Greg Chapman's class, we hit one of his in cisp 300.
Mm-hmm.
Calc 2 was one of the recommended requisites, not a requisite, but recommended classes.
Advisory.
Advisory, yeah.
Yep.
And I think we had 3 Calc 2 students in his cisp 300, which is just hand tracing.
Uh-huh.
They dropped after the first day.
Okay. All right. So do you want to make a point? Yep.
Would it be linear algebra? Or just algebra?
Just algebra in general. What? Huh?
Something to do with loops?
Nope, has nothing to do with loops. It has to do with there are many ways to express the same thing. Okay? No, it's the conditions. Okay, we'll start with conditions, because your first job is unlikely to be, oh, tech, you're the super new green, newbie employee. I want you to start from scratch and write this particular product. That is not going to happen. Okay, my first job at any as a developer is going to be handed a toothbrush, and my job is to clean the bathroom. Okay, that's going to be your first job as well. Okay, which basically translates to, okay, here's our existing code base. Okay, 500,000 lines or something along that line. Okay, and by the way, somebody just called in, the program crashed in this particular condition, and your job is to fix it. Okay, that's very likely to be a first type of first assignment for somebody who's just joining a company, for several reasons. One, this is going to force the new employee to understand the existing code, which is really important, right? And this is also a good test, because if someone says, oh, I don't want to do this, I just want to do new code development, that person can go somewhere else. Okay? But in the process of understanding the existing code, okay, you have to be able to read the way other people express conditions and values. Just because I think it's the best way, this is the best way to express this condition, doesn't mean it is the only way to express that condition. Does it make sense? So somebody else is very likely to use an equivalent but different way to express the same thing. So where algebra comes in handy is you now can look at how the other person expresses it, and you know exactly what it means, because you know the equivalency of those expressions. And that's why algebra is super important when it comes to coding, unless you're encountering some kind of weird program where there are no expressions anywhere. No Boolean expression, no expressions of any integer value. Yep.
I was gonna say, I also feel like it gets scaled up in the sense of it's not just an if statement that's different. Like you have an overall task you're trying to accomplish, and someone just does it way different than you would even think of.
Yep.
Being good in algebra help with algorithms.
It helps with algorithm. Are you talking about the design of an algorithm, or just following an algorithm? The design of an algorithm is actually quite a bit more complex than just to understand it, because we can read, let's say, quicksort, okay, or bubble sort, and kind of get a feel of how it works. But if you have no exposure to any sorting algorithm and you're asked to write a sorting algorithm, that's not easy. That's actually a pretty complex task. It involves a lot of what I would call abstraction. Basically, you would do something by hand a few times, and then you're trying to figure out, okay, what is the underlying structure of instruction that let me complete that particular task. So that's actually kind of difficult to do. All right, well, we're down to question number 5 of 5, the last one. So in this question, let us define x to be the set of all non-negative integer powers of 2, such as 1, 2, 4, 8, 16, 32, and so on. Okay, so I'm using examples so that people know what I mean by non-negative integer powers of 2. Because if I just say powers of 2, well, what about 2 to the power of 0.5? Well, that's technically a power of 2 too, so I got to limit to integral powers of 2. But then what about 2 to the power of -1, which is 1/2? That's an integer power of 2, but that's not my concern either. I just want the non-negative one, starting with 0. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so on. And then somebody's going to ask, then why didn't you just say that? Why didn't you say that, it is 2 to the power of I, such that I is a non-negative integer? Because then I would have given you the answer to many of these questions already. Okay, so that is why. Okay, so keeping that in mind, we answer these questions. Evaluate for there exists n lowercase in natural numbers such that it is not the case that n is an element of x. Okay, what is it asking? Do we have a natural number that is not a non-negative integer power of 2? There should be a lot of those. Like what? 3, right? 5, 0. Okay. So the answer is yes, this is true. And because I'm looking for a counter example to make that true, well, okay, I'm looking for something that is not in X, right, to make it true. So all you have to do is to say when n equals to 0, n is an element of n is true, but n is an element of X is false. Okay? Now, if you don't like to say blah, blah, blah is true, blah, blah, blah is false all day long, you can just say that n is an element of n n is in n, but n is not in X. Okay, you can just say that. So there's a simplified version to say exactly the same thing. Yep.
Mine, for example, I put like n when n is like odd numbers greater than 1, and then I just wrote the notation like.
Yeah, that works. Yep. Yep, so that works. All right, so the second one says, evaluate. There exists lowercase n in X such that it is not the case that n is in natural numbers. Okay, and I'm asking you, is that true or not? Can I find a non-negative integer power of 2 such that it is not a natural number? The answer is false. Okay, so we answer false first. And because, so this is where things can be simple, can also be kind of difficult. Okay, if you want to just say, all non-negative powers of 2 are integers or are natural numbers, fine, I will take that as an answer. Okay, so that's the easiest one to answer this question, is to say all non-negative powers of 2 are natural numbers.
Could you just say all of X is in N? There's nothing in X that's in N?
You can say that. Yep, it's kind of the same thing. But it's a chicken and egg thing, because how do I know this? How do I know that all non-negative powers of 2 are natural numbers? How do I prove that in return?
Make a function to map it.
No. The function is about equivalency of cardinality.
Well, but it also proves that too.
No, it does not. No. Go ahead.
An expanding power function is like a multiplication by
Yep.
addition of integers n times depends integers always.
So what you're mentioning, when you say expansion, what goes through in my mind is proof by induction. Now that is a proof technique that we have not been introduced yet, so I'm not expecting anyone to use proof by induction to prove that every non-negative power of 2 is a natural number. Okay? So when we get to proof by induction, if somebody can remind me to prove this particular one, we can talk about it then. Okay? But at this point, we can just say that. Okay? I'll take that as a 100% answer. Part 3, evaluate X is a proper subset of N and explain your answer. Okay? So first of all, is it true or not? It is true. Okay. And it is because
N minus X is not empty.
okay, very good. It's the other way around.
Or
Everything in N that's not in X is not just that. I think I said that right.
And that too, yep. And X is a subset of N. Yep, okay. So this part is important, okay? That we have something in N but not in X is important to point out in addition to X is a subset of N. Because it's a proper subset of N requires this part here, that you have at least one thing in N that is not in X. Yep. Oh, okay, gotcha. All right. So then the next question asks, can you find a bijective function f that uses X as our domain, and it uses N or the set of all natural numbers as the codomain? If so, what is the mathematical definition of f? And I give you a clue of f of x equals to blah, 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 blah. Okay, so what would that be? In other words, if I give you 16, okay, how do you map 16 back to 4? How do you map 32 to 5? And so on. Yes? Exactly. Okay, so that would be the easiest answer to this question. Log base 2 of x. Okay? But if you guys are trying to test this log function using the concrete examples, you will find that, hey, log 2 is not on my calculator at all. So, well, you can use, which then equals to the natural log of x divided by the natural log of 2. There's a whole bunch of ways to express it, but they boil down to the same thing. Are we good so far? Yes?
How I read that part of the question is x mapped to n, can it be a bijective function? Can
What-
you find a bijective?
It's moving to that direction.
Yeah,
Yep.
I answered the other part.
Oh, but you forgot about this part?
Yeah. Cardinality of x equals cardinality of n.
I see.
And that is false because x is smaller than all natural numbers of n.
That's the whole idea of this question is weird. It is weird. Okay, but getting back to here, okay, yeah, what is the mathematical definition of f inversed? So if you know that log 2 of x is the forward function, what is the reverse function? What is the other way around? 2 to the power of x. Okay? Wait, so now we have a bijective function, right? So now it's, so if so, so this is, so I don't have to say if not, okay? Because the answer is yes, we definitely have a mathematical definition of a bijective function that will bring us from x, all the non-negative powers of 2, to the natural numbers. So now the question is, we're moving on to here. Evaluate this thing. Okay, I forgot to open parenthesis. And it's asking you, explain your answer. First of all, what is the answer to that question? In other words, what should I put here? It's true, okay? Because it's an equality check. That's all it's saying, okay? It is. That's why I put the extra parentheses here, because I'm not asking what is the cardinality of x. That is not what I'm asking. I'm asking, does it equal to the cardinality of natural numbers? That's what I'm asking, true or false. Okay? The answer is true, and the answer is because there's at least one bijective function between x and n. Yep. Because f is bijective. If you want to be short, that will suffice, because the way we define the way we define f is x is the domain and then n is the codomain already, so you don't have to repeat that. Are we good so far? And I think that's the end of, sorry?
I just need to read the question better.
Oh, you just left some. Well, for the first part, you will get partial credit, and that's why I broke a question down to smaller components and smaller steps. So if you get the first part, you'll still get partial credit for the first part. If I just jump all the way to the bottom one here and ask this one without all the previous questions, then either you get it or you don't, right? But the way I structure it, I was trying to make it so that, well, see how far you can go, and you can get partial credit up to that point. And that was it. That's the whole test. So what do you feel now? Better, worse, indifferent? It is what it is. All right. I don't think this one is particularly difficult of all the tests that I have, made up, for up to this point. Are there any questions? So, Yes. So once I scan all the exams, I will bring it back to my office. Whether I remember to bring it back to class is a different question. But I will bring it back to the office, and you guys can come to my office to get it, if you want to, or you can remind me to bring it to class. Then I can just kind of hand you guys the exam. But that's also the part where it will take a little bit of time because I have to destaple each one, run it through the scanner, and then restaple. There's a lot of actual paper handling involved. But then I have your exam archived on my Google Drive for eternity. You can, if anyone has grandchildren and want to say, I want Professor Tech, if you're still around, I want my test back so I can show my grandkid, what kind of difficult stuff I have to study when I was in college. Yeah. It will still be on the internet. That's the whole thing. Things that are now on the internet will stay on the internet pretty much from here on. All right. So if you don't have any questions, we're good. If you do have questions, but you don't want to ask those questions in class, that's okay too. I got office hours right after class. So you can talk to me after class if you have any comments. Yep, go ahead. No, you can keep it. Yep, because I make new questions every semester. And I use a program to generate these questions too. So for each semester, I refine that program a little bit, and also introduce some additional variable stuff in the questions. So to me, that's kind of fun. Yeah, that's what I like to do. All right, so that's your exam. And without any questions about the exam, we can talk about COBOL. Or we can go back to the class. Okay, let me see. So we're going to get back to relations. Are there any questions about relations from our discussion before? Okay, so let's go back quickly to the discussion of relations. And then what we'll do today is to point out an actual relation that is totally ordered. Okay, so you guys have an example of, so can you give me an example of something that is totally ordered? Yep, it's actually quite simple. So we are now back to relations. And I'm going to open up the homework assignment so that you guys can work on that one. All right. There we go. All right, so we are going to skip all the way to total ordering because we just want to say, well, in real life, do we have relations like that? Relations that are reflexive, asymmetric, transitive, and also comparable over X, meaning that if you pick two things from X, then we can say ERF or FRE. Okay, so everything relates to something in some way. Okay, that's basically what it's saying. So as it turns out, one particular operator that you should be somewhat familiar with already meets all of those requirements. So I'm going to use a notepad for that purpose. There we go. As it turns out, this meets all the requirements. When you define less than or equal to over all integers, over all, basically all real values as well, it meets all those requirements. Okay? So let's check it. Okay? So let's check whether less than or equal to, does meet all of those requirements when x equals to the set of all integers. Okay? So the funny looking z, which I cannot do using just a regular text editor, usually denotes the set of all integers. Okay, so but right now I cannot do the funny thing with the bars and whatnot, so I'm just going to use letter z here. Okay, so I'm claiming less than or equal to as a relation over Z is total ordering, or the relation itself is a total ordering relation. Okay, so let's check all of these things. Okay, is it reflexive? Okay, what does that mean? If I pick any integer, okay, so pick any integer I, if I is in Z, can I claim the following? I is less than or equal to I. And we say for all. Is that true? Choose any integer, and is that integer less than or equal to itself? Yes. Okay, very good. So that makes it reflexive. Okay. We don't need symmetry, but we do need asymmetric. Okay. Is it asymmetric? Antisymmetric. Sorry. Keep mixing that up. Is it antisymmetric? So does anyone remember the definition of antisymmetric? I'm not expecting you guys to remember that because you have to study for the exam, right? And then you took the exam. So now we're getting back to relations, which is stuff that we talked about, what, more than 2 weeks ago? So I'm not quite expecting all of you to remember that, okay? So it basically says for all E and F in this case, a set of integers, all it says is E is less than or equal to F, and F is less than or equal to E, implies F equals to E. Okay, let me add some additional parentheses to make it clear what is the left-hand side of the implication and what is the right-hand side of the implication. So is that true? Okay, I see. Okay, let me move that thing a little bit to the left. There we go. Okay, so is that true? If I choose any two integers, okay, any two, okay, they can be the same to begin with, they can be different, also. E is less than or equal to F, and F is less than or equal to E, implies F and E are the same thing. So let's check a few things, okay? Let's check a few things where, especially things that intuitively does not make sense, okay? So we'll say E equals to 1 and F equals to 3. Is that okay? 1 and 3 are integers, right? So I can choose E to be 1, F to be 3. 1 is less than or equal to 3, true, right? 3 is less than or equal to 1, not true. But that's okay, because true and false is false. If the left-hand side of the implication is false, I don't even care about the right-hand side. That is true already. It makes the implication itself true. Is that okay? I can also choose E and F to be exactly the same thing. Okay, so let's say E and F are both 2. 2 is less than or equal to 2 is true. 2 is less than or equal to 2 is true. True and true is true. So now I do have to take a look on the right-hand side of the implication. 2 equals 2 is also true. So we got true implies true, which is true. So that's kind of my quick demonstration of why this expression is true for this relation defined over integers. The next one is transitive. Okay, is it transitive? Okay, I took that extra close paren from here, put one back here. There we go. So how do we define whether something is transitive or not? For all, so this time we got E, F, and G in Z. E is less than or equal to F, and F is less than or equal to G, implies E is less than or equal to G. So once again, let me group these two with its own pair of parentheses so it's super clear what we are talking about. Does that make sense to you? Okay, so that's why it is also transitive. But remember, these three alone will only define the relation to be partially ordering, not total. Okay, this is partial ordering, not total ordering. So what makes it total ordering is the last one. Okay, so let's take a look at the last one, and we'll take a look at the mathematical notation first, and then we'll switch back to notepad. So this is what it means to be comparable over X. Okay, let me zoom in so that you guys can see better. Okay, so this part here is the extra requirement. Okay, for all EF in whatever set that we define the relation over, ERF or FRE. Okay, so let's see if we can translate it back to our example. And is it comparable? Okay, so we say for all EF in Z as integers, E is less than or equal to F, or F is less than or equal to E. Does that make sense to you? E and F are integers. If I pick any integer to be E, any integer to be F, does it make sense to you that E is less than or equal to F, or F is less than or equal to E? Yep. So that means less than or equal to defined over integers meet all the requirements of total ordering. And that's why less than or equal to as an operator can now be used as a comparison operator for sorting algorithms. Is that okay? So if less than or equal to, if the entire module, okay, is only really here to talk about less than or equal to defined over integers, this is like total overkill, right? But it's not unlike me to overkill something, usually, okay? But this whole section is not an overkill, because in programming, instead of comparing integers, other times you'll be comparing things that are not intrinsically, you don't intrinsically know whether it's partial ordering or not. Remember last time we were talking about the ranking of gamers. So the logic that you choose to use to compare and rank gamers is up to you or the company that you work for. Okay? Do you know whether that is at least partial ordering, which is good, okay? But you cannot use partial ordering to say this is our gamer of the month, because partial ordering can leave certain things behind, like, well, we know this person is better than all of these, this person is better than all of these, but we have no way to compare these two. Okay? That's partial ordering can leave you in a state like that. In order to have one single person as gamer of the month, you need total ordering. So now the question is, can you look at your overload operator for less than or equal to compare objects of the class that you define and say whether it is a total ordering or not? Does it have all of these properties? That is a question that you have to ask. Is that okay? Does everybody know how to relate these concepts back to practical stuff that you have to do as a developer? And I think this is applicable more than ever these days, because before, we have ranking, we have ordering. Even COBOL, okay, has ordering. SQL has ordering. Okay, everything depends on ordering. But when we are ordering in COBOL, okay, let's say we are processing social security checks, okay, that's usually just ordered by social security numbers, okay, or something that we know is, oh, these are just numbers. Totally, we understand they can be totally ordered, okay. But these days, when we are talking about social media, okay, when we are talking about search engines, we need to do ranking on things that are not really simple, okay. Okay, these two sites, they both contain these keywords that somebody has searched for in a Google search. But when you display results of a Google search, it has to follow a particular order, right? So now the question is, which one should come first? You need a mechanism that gives you total ordering, because a partial ordering won't give you that ability. Is that making any sense? And we are, we apply ranking, a lot more than before now, because you can go to Facebook, okay, whose wall should I display first? What do you think the person, the user, is going to be most interested in? Those are all about ranking. They are all about sorting, okay? And if you want to sort anything, you need total ordering. And if you need total ordering, you need to make sure the comparison operator satisfies all of these requirements. That is how we tie theoretical stuff like this back to programming. Well, at least how I would tie it back to programming. But I think those are all realistic problems that we have to solve. So is that good so far? Okay. So I just want to kind of fast forward a little bit so that we know what we'll be talking about on Wednesday. It's just a sequential order. So on Wednesday, we're moving on to propositional logic. Now that is fun stuff. The propositional logic module, there's only one module, okay? Doesn't sound like a lot. But in it, we also have conjunctive normal form, resolution, and proof by contradiction. So even though it is one single module, the number of concepts involved, one, is kind of abstract, and two, there are multiple concepts involved, okay? So it becomes even more important for you guys to read ahead of me, at least to get a general idea of how those concepts relate to each other, okay? So focus on the forest and the shape of the tree. Don't focus on the pine needles when you're reading, okay? Because when we're in class, I can go through the pine needles. All right? So I'll see you guys on Wednesday.
I got the okay from Randy about using the video camera.
Yeah, he told me about that. He liked that idea.
Yeah, and he